today we're going to do one more example of Polya counting. And the thing I'm going to count is colorings of this kind of arrangement of cubes. So I'm just going to call this a windmill. All I mean is this particular arrangement of 12 cubes in 3 colors. So in this case, red, white, and blue. So in particular, I want you to interpret this as a 3-dimensional object, which means I'm going to allow as a symmetry that I turn it upside down. So something like, well, that didn't go well, but imagine I had turned it upside down and that worked. So we're going to have to interpret this as a Polya enumeration theorem problem. We're going to have to figure out what the nodes are, what the group of symmetries is, and then we're going to have to calculate for each of those symmetries what the cycle number is, and then this formula will tell us what this is with m being 3. So that's our plan. All right. So what is the thing we're coloring? Well, the thing we're coloring is something that has this particular shape. So that, and then this, like that. And so our nodes correspond to these squares. So our set n is 1 through 12. Then we have to think about what the symmetries of this arrangement are. So the first ones that come to mind are the ones that have shown up a lot in the previous ones, namely the rotations. So I can rotate this thing any number of times from 0 to 4. So I can, again, do nothing. I can rotate it 1 click, rotate it 2 clicks, rotate it 3 clicks. Okay. But that's not all the symmetries, because I'm now allowing us to flip this arrangement upside down. And so the way I want to do this is I want to label the flips by what axis they're flipping over. So in particular, if I flip over this line, I'm going to call that flip 1. And very similar to flip 1 is going to be this, where I flip over that line. So that's going to be flip 2. So flip 2 is that, flip 1 is that. Okay. There are 2 more flips that you can see corresponding to the diagonals. So I'm going to call that flip 3, and that flip 4. So let's go ahead and throw those in here. Okay, and I think you can convince yourself that's it. That's all of the symmetries that this arrangement has that I want to keep in mind when I'm counting this thing. So there are in total 8 symmetries. And I want to, again, count the number of cycles. So let's figure that out for each of these things. So for the identity, I think we know how that's going to work. Nothing's going to move, so there's going to be 12 total cycles. Okay, so let's think about when I take the cycle rotation of R, or when I take the cycle number of a single rotation. So let's think about where 1 can go. 1 goes to 6, goes to 12, goes to 3, goes to 7. 1 would go to 7. Yeah, 1 would go to 7. Okay, so those 4 all form their own orbit. Similarly, 2 and 10 and 11 and 3, those all form an orbit. And similarly, 4, 5, 9, and 8, those all form an orbit as we do this. So that means there's 3 total orbits. 1 for the middle 4 squares, 1 for the left side outer square, and 1 for the right side outer square. Okay, so that means C of R is 3. And by the same logic, because r cubed is actually just rotating counterclockwise instead of clockwise. C of r cubed is also going to be 3. In fact, the orbits will be exactly the same. Okay, last up, let's think about C of r squared. C of r squared now, we're looking at what happens to things if I rotate twice. So 1 will go to 12, and then back to 1. 2 will go to 11, and then back to 2. In fact, actually, everything, if I rotate twice, will swap places with something else. And so these things all end up in pairs. And so, in particular, the number of cycles for r squared is 6. Okay. So, now we have to think about the flips. So I'm going to put this down here so we can keep in mind which flip is which. Okay, and I want to count the cycle number of F1. Okay, so that is this. And by symmetry, that's also going to be the cycle number of F2. I'm just going to note in advance. And so when I flip across axis F1, 1 and 2 flip, 4 and 5 flip, 8 and 9 flip, 11 and 12 flip, 3 and 6 flip, and 7 and 10 flip. So that is, everything gets paired up, and there end up being 6 total orbits, or 6 cycles, whichever you want to say. The same thing happens, you can convince yourself if you want to actually check for F2. These 6 each get paired up with exactly one of those 6. Okay, again, by symmetry, we can look at F3 or F4. They're going to be the same. Now, I want to note right away that F3 is not going to be the same as F1 and F2. And the reason for that is that when I look at F3, it actually preserves 5 and 8. These are both fixed points under this symmetry. And so that means each of 5 and 8 are going to be in an orbit unto themselves under F3. And then what happens? Well, 2 and 6 get paired up, 9 and 4 get paired up, 11 and 7 get paired up, 12 and 3 get paired up, and 10 and 1 get paired up. And so how many cycles is that in total? That ends up being 7 cycles in total. Okay. So that gives us all of our cycle numbers. And so once we have all of our cycle numbers, we can pretty straightforwardly apply our new favorite Polya enumeration theorem. So, namely, the number of colorings in, again, remember these 3 colors, the number of colorings will be 1/8 of, and then so 3 to the 12th, plus 3 cubed, plus 3 cubed, plus 3 to the 6th, plus 3 to the 6th, plus 3 to the 6th, plus 3 to the 7th, plus 3 to the 7th. Okay, and so you can type this into a calculator, and then you'll figure out what number this is. In fact, I'll go ahead and do that right now for you. Let's see. 1/8 times 3 to the 12th plus 3 cubed plus 3 cubed. Okay, and we will get that, in fact, the number of these windmills works out to be 67,257. That is the total number of visually distinct ways to arrange these cubes. All right. For the homework, I'm going to ask you to think about how to make a very similar structure and how many ways there are to do it. But instead, I'm going to have, instead of the one we did today, I'm going to have you make structures that look like this. So that is, they look sort of like a very blocky letter I. So this is a total of 9 cubes. So what I'm going to ask you to do on the homework is I'm going to ask you to tell me how many ways there are to make eyes of this sort out of 3 colored cubes that are visually distinct. So you'll have to work out, again, what the symmetries are, and then you'll have to calculate the cycle number for each of those symmetries, and then apply the formula. And then you will have your answer.